Now I want to go back to something that kept happening in the last video. When we had sine of kt over negative e to the st, when we evaluated as t went to infinity, we knew that that was going to become a 0 because the numerator was, well, bound between negative 1 and 1. Before that, when we had a t over e to the st, we knew that was going to go to 0 as t went to infinity because the exponential in the denominator was going to outpace the t in the numerator. This situation will always happen if the function that we're transforming, or the function that we're talking about, eventually gets outpaced by the exponential function as t goes to infinity. And that's actually a characterization of what we call exponential order. A function f is said to be of exponential order if there exists constants c, a positive m, and a positive t, such that the absolute value of f of t is not bigger than me to the ct for all t lowercase greater than t uppercase. Dude, what? Okay, what this says is a function is of exponential order if you can construct an exponential function that eventually is always bigger than the function, in magnitude anyway. In other words, it's of exponential order if it doesn't grow faster than an exponential. You're going to hear these words exponential order quite a bit, and this is what it means. When we saw the definition of the Laplace transform, we saw that the integral defines the Laplace transform provided the integral converges. This next theorem basically tells us when that's going to happen. A sufficient condition for the existence of a Laplace transform is that f is piecewise continuous on the interval from 0 to infinity. That means it can't be a tangent and go off to infinity or anything like that. And of exponential order, doesn't grow faster than an exponential. If those are true, then the Laplace transform of a function exists for some value of s greater than c. I tell you what, for our work, we're never going to care what the value of s is. The reasons for that will be kind of apparent as we go. For now, we're going to look at a proof of this thing. This references exponential order, so we're going to call up the definition of exponential order. As we just saw, f is of exponential order, means that there are constants c, positive m, positive uppercase t, such that the absolute value of f of t is less than or equal to me to the ct for some value of lowercase t that's greater than uppercase t. I didn't really get into this t greater than t business. What that's telling us is that there exists on the t-axis some value of t. And if we consider the exponential function, it's going to grow like that, then f of t is always less than the exponential function as long as we're to the right of some number. So f can start out huge and then eventually become less than the exponential function, and that'll make it of exponential order. So that's all that's meant by this t greater than t business. Okay, that was a side note. We're back to this proof here. And we're trying to say when this integral is going to converge, right? So the Laplace transform of f of t is equal to the integral from 0 to t of e to the negative st times f of t dt, plus the integral from t, that's uppercase t in both cases, to infinity, e to the negative st f of t dt. What have we done? We've split the interval over which we are integrating from 0 to t and then from t to infinity, where t is that uppercase t that we saw in the definition of exponential order. Let's say that this is integral 1 plus integral 2. Integral 1 is the first one with limits from 0 to uppercase t. Integral 2 is the second one with limits from uppercase t to infinity. We're trying to consider under what circumstances the integral converges. Well, f is piecewise continuous, which means it doesn't blow up to infinity or anything. E to the negative st is a continuous function. So if I evaluate a product of two continuous functions from 0 to t, or f of t piecewise continuous, then I'm going to get a finite number. So integral 1 exists because f of t is piecewise continuous. That's why it's in the theorem. We should probably use that fact in the proof at some point. The second integral, I2, is equal to the integral from t to infinity of e to the negative st times f of t dt. I'm rewriting it for a reason. And we have this inequality here that the absolute value of f of t is less than or equal to this expression here with the exponential. So let's make this the absolute value of the integral. And we can say it's less than or equal to the integral from t to infinity of e to the negative st, and then replace the absolute value of f of t with m e to the ct. And of course that integral is with respect to t. Now, because we have I2 is less than or equal to some integral here, if we can show that this integral converges, then we will know that the I2 integral converges, and then the whole original transform integral will converge. For the integral we're looking at now, we can factor out the m. We have the integral from t to infinity, and then we can combine the exponential factors. I'm going to factor out the negative that's in the exponent here, and we have e to the negative quantity s minus c times t dt. Integrating that is going to give us negative m over the quantity of s minus c e to the s minus c times t. I put it in the denominator because, the exponent was negative. And that's going to get evaluated from t to infinity. As long as s is bigger than c down here in the denominator, this is going to converge, because when I put infinity in place of t, that will zero out the term, and then putting uppercase t in place of t, we just get a finite number. So it's finite as long as s is greater than some number c. And if you're wondering about that, don't worry, it was in the statement of the theorem. The Laplace transform exists for s greater than c. So we have that the integral I1 converges, the integral I2 converges, so the integral I converges. And we've shown that the Laplace transform will then exist. Now we were told this is a sufficient condition for existence, so as long as f is piecewise continuous and it's of exponential order, then the Laplace transform exists. It's not a necessary condition, meaning we can have a case where we have a Laplace transform that exists for a function that is either not piecewise continuous or not exponential order, something like that. We'll see an example of one of those toward almost the end of the chapter. Continuing our exploration in theory and exponential order, we have another theorem, the behavior of f of s, the Laplace transform of a function as s approaches infinity. Now is probably a good time for me to talk about that notation. The Laplace transform of lowercase f of t is represented as uppercase f of s. Remember, I told you a function of t goes into the transform, a function of s comes out of the transform. And to connect what comes out with what goes in, we use the same letter but different uppercase, lowercase. And we actually see that notation present in the statement of this theorem. If f is piecewise continuous on the interval from 0 to infinity and of exponential order, and if we're calling uppercase f of s the Laplace transform of lowercase f of t, then the limit of uppercase f of s, the transform, is 0 as s approaches infinity. Let's go back to the transforms that we've seen. Sine of kt, we've got k over s squared plus k squared. Cosine of kt, its transform is s over s squared plus k squared. And in fact, for every single one of these formulas, as s approaches infinity, the expression involving s goes to 0. This theorem codifies that, and we're going to prove it. F is of exponential order. Let's write down what that means. There exist, I'm using math shorthand, that uppercase backwards E is there is or there exist. We're going to tweak the definition of exponential order just a little bit. A gamma, that's the lowercase Greek letter gamma. A number uppercase M1 that's positive, and an uppercase T that's positive, such that backward curly E means such that the absolute value of f of t is less than or equal to m1 e to the gamma t for lowercase t bigger than uppercase t. Since f is piecewise continuous, On the interval from 0 to infinity, we know that f is bounded. By definition of being bounded, that means that the absolute value of f of t is less than or equal to some constant. We'll call it m2. And then we're going to express m2 as m2e to the 0t to bring in the exponential order business. Well, now we've got two exponent coefficients going on. One's gamma and one's 0. And we have two bounding numbers. One of them is m1 and one of them is m2. We want to satisfy everything right now. And a common way to do that in math is to do something like let uppercase m, no subscript, be the maximum of m1 and m2. And then we'll let c be the maximum of 0 and gamma. Why did we want to do that? Well, we're talking about the Laplace transform f of s. And that equals the integral from 0 to infinity of e to the negative st times f of t dt. I want to use the exponential order stuff, and so we're going to absolute value the Laplace transform and f of t. And like we saw the last time, we're going to take that absolute value of f of t and use the inequality that describes exponential order. So we have the integral from 0 to infinity of me to the negative st times e to the ct dt. Again, uppercase M is the maximum of the two m's that we had running around, and c is the maximum of 0 and gamma. So all the conditions that we care about up here are satisfied because of that step. Well, this integral is going to evaluate to m over s minus c as long as s is greater than c. C is just some number. We don't care what s is. But what we have is, as s approaches infinity, we have a finite numerator and an s in the denominator. So the absolute value of uppercase f of s, the Laplace transform, of lowercase f of t is going to approach 0, and that's what the theorem claimed.